So we'll be using a lot of complex numbers in our calculations for circuits soon, now that we're going to start to get into frequencies. And so I thought I'd give a little primer on how we do arithmetic with complex numbers. So to begin with the definition, a complex number is defined by adding a real part and an imaginary part, and the j of the imaginary part is defined to be the square root of minus 1. We can treat that pretty much as a vector in the y direction if we think of real and imaginary parts, and then the a is the real part and the b, which multiplies j, is the imaginary part, and therefore this point c is the same as that number there. And if we have that number c, we can take the real part and just get a, we can take the imaginary part and just get the b, and so that sort of defines the complex number on the Cartesian plane in Cartesian rectangular coordinates. Note that the imaginary part of c is a real number b. We can also express the complex number in polar coordinates, and to do that we use the Euler formula. The Euler formula says e to the j theta is cosine theta plus j sine theta. In other words, the exponent raised to an imaginary number has a real part, which is cosine theta, and an imaginary part, which is sine theta. Therefore, we can express any complex number as a factor, which is the magnitude of c, but that's a real number. It just says how long the thing is, rotated then by e to the j theta. So the theta gives you the rotation around. The magnitude of c is just a squared plus b squared, or the length of that line in the Cartesian sense. Right, so the length of c, the absolute value of c, the magnitude of c, is the square root of a squared plus b squared, and the angle theta is just the arctangent of b over a. In other words, the tangent of theta is b over a. So that just defines how we can think of a complex number. Sometimes it's easier to use the a and the b, sometimes it's easier to use the theta and the magnitude. Now, when we add complex numbers, it's really quite easy. It's just the same as with real numbers. The only difference is that we'll want to gather all the terms that have a j, the imaginary unit, into one term, the imaginary term. So if I have a complex number a, capital A, equals a plus jx, and complex number b equals little b plus jy, then when I add them together, I just write everything down, and then I can rearrange the terms using associativity, take the real parts, put them together, take the imaginary parts, put them together, and then I have the real and imaginary parts directly. This is exactly what happens when we add vectors, and so if I represent this by a and this by b, the fact that I add the real parts and add the imaginary parts just makes for a plus b to be this line in exactly that angle. Or we can say that, if we're going to take the magnitude of capital A plus capital B, we take the real parts, add them, and square them. We take the imaginary parts, add them, and square them, and then take the square root of all that. The phase of this, in other words, the angle, then, is just the arctangent of the imaginary parts added over the real parts added. So, adding complex numbers, just like real numbers, we just have to keep the imaginary terms separate from the real terms. Now, for multiplying, we do it exactly the same as real numbers, however, it will not be a vector. So, again, here's my two complex numbers, same as on the last page. If I multiply the two, I just write down each of the two expressions in their real and imaginary parts and multiply the all out. So I get a times b, I get a times jy, I get b times jx, and I get jx times jy. Now I regather the terms here, and I can gather the two terms with j here, and notice that j squared here provides a minus sign, and that the result is real. So my real part will then be ab minus xy plus j ay plus bx. Now in this case it's much simpler to interpret the result in polar coordinates, whereas if I multiply two complex numbers, I just multiply their magnitudes, and then I multiply both of the exponential parts. But remember, if I multiply exponentials, I add what their powers are. So in the end, all I do is I multiply the magnitudes and add the phases. And notice that if both A and B have magnitude 1, all I've done is rotate it around the unit circle. E to the j theta is all I get. Notice that in this scheme, it helps to know a few identities. Square root of j, we can figure out using this because two numbers have to multiply to give j in that case. So we write that as a e to the j theta, and then if we square the square root of j, we just get j. And here we explicitly carry it out. We multiply a by itself, and we double the theta, and then we see that we have to have a equal 1, a squared is 1, a is 1, and that we need 2 theta to be pi over 2 to get halfway around, quarter of the way around the circle. So therefore, the square root of j has a magnitude of 1 and a phase of pi over 4. Now, if we take the cosine and sine of pi over 4, they're both square root of 2 over 2. So that means the square root of j must be 1 plus j over the square root of 2. The square root of 2 over 2 is the same as 1 over the square root of 2. Finally, we want to define the operation of taking the conjugate of a complex number. All it is, when we take the complex conjugate, is we change the sign of the imaginary part. So if we have this complex number, a star is how we represent the complex conjugate, and you'll notice we've just changed the sign of the imaginary part. The reason we want to do the complex conjugate is it makes defining the magnitude very simple. If we multiply a complex number by its complex conjugate, we can see that when we multiply it out, we get the imaginary terms will always cancel, and the minus sign fixes the j squared minus sign, and just get a squared or b squared, which is the magnitude of a squared. We can use this to make it easy to divide complex numbers. In that case, it's often still useful to make a real part and an imaginary part, but to get that to happen, we have to make the denominator completely real. So if I divide two complex numbers, c and a, I might get something like this. And so I want to make the denominator real, so I multiply by 1 in the form of a, the complex conjugate of a, over the complex conjugate of a, and then I multiply that out, and then therefore I see that I have a real part and an imaginary part. I can use that, by the way, to find what 1 over j is. And so the complex conjugate of j is just minus j. So here I multiply by minus j over minus j. Minus j squared is just 1. And therefore 1 times minus j. So 1 over j is minus j. A very useful thing to remember, and will come up fairly frequently.